Okay, well, we'll make a start. Hello, everyone, and welcome to the Learning Dissemination event for the A&M Balancing Coordination Demonstration Project, known as ABCD. I'm Jenny Woodruff, and I've been involved in project management of ABC on behalf of National Grid Electricity Distribution, or NGED. We're expecting today's session to last approximately somewhere between an hour and a half, and we are recording today's session, and we'll publish the recording and the slides on the NGED Innovation website after today. There'll be an opportunity for questions at the end of the presentation. So we're using Zoom today, so there's a question and answer facility. So if you have a question, can you use that rather than the chat? That'll make it easier for us to pick out the items there. However, if you don't think of a question till the end of the session, don't worry, I can unmute you and we can use the hands up facility to come to you then. So we can come and get your questions that way at the end. So thank you very much. So today we're going to start with introductions before moving on to explain how balancing services and A&M systems have the potential for conflict. After that, we'll look at the proposed solution and how it was implemented before sharing the results of the trial. Lastly, we'll cover the next steps before moving on to that Q&A session. So I've already introduced myself. I'm Jenny. I was project manager for the early stages of the project for NGED, and I'd like to introduce David Smith from Smarter Grid Solutions. And that company modified their A&M system to demonstrate how coordination can take place. You want to say hello, David?
Good morning, everyone. Thank you for joining.
Mazza Syed joins us from WSP today. WSP were involved in providing an independent viewpoint, for example, to ensure that the test scenarios selected were suitable and to oversee the system acceptance testing and the trials, as well as assessing the commercial impacts from implementing this coordination method. Do you want to say hello, Mazza?
Hi, everyone. Thank you very much for coming.
And last but not least, the project was jointly funded with National Grid ESO, and Dennis is my counterpart in that part of the company. And his interest is ensuring that his part of the business is getting the required impact from the balancing services that they procure. Hello, Dennis.
Morning, everyone.
Hi. So the background to the project is that we've long been aware of this potential for A&M and other services that require customers to change their demand or generation to have the potential to interact negatively. The balancing services or the balancing mechanism is of particular interest as it's a well-established service and it's likely to grow in volume as more generation comes from renewables. So the project's first objective is to work out the algorithms for coordination between the systems. And as part of that process to determine the algorithms, that helps us to understand the data exchanges that are required to support those algorithms. So we then went a step further and said, what technology do we need to support those data exchanges and how those comms be enabled? Then we wanted to build and test that technical solution with an offline prototype. And finally, we wanted to understand the likely commercial impact of introducing that system-to-system coordination. So as well as the people that I've just introduced, there were other people involved in the wider project teams. I think there's even a couple of names being missed off that, actually. If we move on to the next slide. The project was structured into a series of work packages to deliver those objectives. As I said, the design of the system, testing it out, and a trial phase, and then that commercial evaluation package as well. I'll now hand over to Mazza to take you through the background to the potential for conflict between these systems.
Thanks, Jenny. Thank you very much. So I'll just start off. Thank you, everyone, for joining us today. Just to give you a little bit of context, yes, we all know the power industry is working hard to achieve or to move towards the net zero target. And very recently, I mean, when I was making the slide, I just realized like there's only 27 years to go. So this number keeps decreasing quite quickly. And with this happening, with renewables, the way that we are integrating within the network, we already realize the operation and control is becoming increasingly challenging. With this, we are looking at new approaches that we can have so that we can ensure that our system remains stable as we move towards net zero. And to achieve this extensively and more, we are trying to harness the capabilities of distributed generations that are present within the distribution network, that is, to exploit the flexibility that will be available in the distribution network in the future. Next slide, please. But what does this do? So with the growth of distributed generation, there are two things that we see are happening or will happen in the future. So the ESO will be looking to procure more and more balancing services from distributed generation because they are available. And at the same time, these distributed generations will be under some sort of A&M scheme to try to manage any potential conflict that might arise or any constraints that might be within the distribution network. However, another press dip, yeah. Although this is beneficial for the distributed generation, there are some synergies over here. This also has the potential of presenting a conflict. If the A&M services and these balancing services they are not coordinated together, this will result in increased costs to the customers and also will pose a risk to the security of supply. Next slide, David. So there are a couple of conflicts that might arise, but for this presentation here today, I'll just go through one of them that we've worked through. Consider the sample distribution network, which has two generators, each of these generators G1 and G2 rated at 8 MVA. This part of the distribution network, or that we see over here, is we assume that it is under A&M, and the objective of A&M is to control the power export at the point of common coupling to 9 megawatts. We also assume that generator G1 is non-curtailable, so it's not under the A&M, while generator G2 can be controlled by active network management. We have 1 megawatt of load, we assume, within this network, within this distribution network, and there are no load variations. Next slide, please. So under steady state, under normal operating conditions, as you can see, generator 1 is generating 7 megawatts. Generator 2 is at 3 megawatts. Given that there is 1 megawatt load in the network, the export that we see is 9 megawatts. So the A&M is doing its job very well, was controlling the power export to 9 megawatts. Now, at a particular settlement period, say 10, the ESO issues a command to the generator 1, which is the non-curtailable generator, to reduce its power output by 5 megawatts. In response to this, we see that generator 1 reduced its power output from 7 megawatts to 2 megawatts. Then at the next step, here, now we see that A&M now realizes, because A&M is controlling the power at the PCC to 9 megawatts, A&M sees that now there is enough headroom available and therefore releases generator 2, the headroom for generator 2. As a consequence, now generator 2, under control of A&M, ramps up its power to 8 megawatts. Therefore, in the end, the result, as you see in the graph over here, the power export at the point of common coupling is back to 9 megawatts, which in return means that the impact of this balancing mechanism has been nullified. So this is the conflict that we wanted to demonstrate. Now, as part of the previous Network Innovation Allowance project, 9 solutions were proposed, and these were under 4 categories. The first category was W solutions, which required reconfiguration of A&M schemes. Just another click, yeah. The second set of solutions required improved information exchange between the DNOs and the generators. The third one is the Y solutions, which required changes to the balancing services procurement process itself. And then the final one was coordinating class and A&M systems. Now, all of these solutions were evaluated based on cost-benefit analysis and the technical feasibility of implementation. And based on that analysis, solution W1 was taken forward for proof of concept implementation. And now I'll hand over to David, who will take you through solution W1.
Sure thing. So as we've discussed, we've looked, the solution we have taken forward for the trial was the reconfiguration of the A&M scheme. So the next set of slides, we're going to talk a little bit about what that reconfiguration looks like from a technical perspective, the reasons it's triggered, and the communication architectures we looked at to facilitate that. So the diagram you can see here provides a high-level overview of the interactions between different parties who are involved, and provides a bit of a kind of flow to show what the interaction looks like for the reconfiguration of the A&M. What I will say just now is that when we talk about the reconfiguration of the A&M scheme, for the purposes of this trial, we have called that hold mode. So I'll refer to that as we go through. We'll explain a little bit more detail shortly, exactly what that means, what that looks like. So what we wanted to show here is just the different signals, the different bits of information that's passed between different systems, parties in the overall system. So the important bit of information is understanding what services are being procured and the impact that's going to have on the overall system. So you'll be able to see here the ESO, and this represents the traditional, the business as usual interaction between the ESO and the service providers on the distribution network. So service providers provide a physical notification to say what their baseline is essentially going to be over the range of settlement periods they're involved in, and the ESO is able to send out bid offer acceptance instructions when they need to be actioned. And essentially, what we've discussed here is that as well as that information flowing between the ESO and the service providers, the information will also be passed down to the DNO. And that allows the DNO to calculate and work out when conflict is possible. So when those balancing requests can potentially conflict with the A&M schemes. So that requires a little bit of work on the DNO side to understand what areas the balancing requests affect, whether there's an A&M scheme active in that area, and then work out exactly where the work out whether that's going to potentially conflict with the A&M scheme itself in that area. The DNO can then send a hold signal. So hold signal is a mechanism used to resolve the conflict, and that's sent down to the A&M system. And the A&M system for the area that the hold is actioned on will be essentially performing its constraint management function as normal, interacting with the DNO to send out commands and get measurements and essentially control the DER in the network, which it has control over. So this slide talks a little bit about the situations where we have the calculations used to work out whether a conflict is possible. So essentially, the conflict we are looking at here, as was previously described, is when the ESO is sending out a generation turn down request. And essentially this table on the left is essentially the calculation, the logic that is used to work out whether there's a generation turn down request requested. So the DNO system here would look at the bid offer acceptance instruction to understand whether it is a decrementing request. It looks at the physical notification to understand whether the DER would originally be exporting, and then it looks to make sure that the instructed megawatt is less than the physical notification, which would indicate this overall a turn down request. And as a result, if all of those are true, then it would send out a hold mode signal to the A&M system. And if any of those are not true, then it's not potentially not a service that is going to be causing conflict, and therefore hold mode would not be enabled. And so this kind of calculation would be run for each of the service requests that come in to the DNO, and it would have to understand exactly, assign those service requests to different A&M schemes and understand the link between those. The diagram you see on the right of the screen here just essentially trying to represent the DER, show which DER would be controlled, managed under that hold mode. So essentially the blue subset is the DER which would be controlled. And essentially what we're trying to represent here, there is a large, the superset is all the DER on the part of the distribution network the A&M system operates on. The smaller subset here is the DER under A&M control, and there's a little bit of overlap with the other small subset, which is the DER that are participating in ESO services. And the main thing we're just trying to represent here is when the A&M system goes into hold mode, it's only going to manage those DER which are not providing ESO services and which it would normally have control over. So what actually is hold mode? What does it look like? So as a headline, hold mode aims to maintain the overall effect of the flexible DER on the ESO DNO boundary for the duration of the ESO service request. So essentially, looking at the overall impact of the flexible DER that are under A&M control and making sure that doesn't increase in any great way that would nullify or degrade the ESO service request. So the way it's been implemented has a couple of benefits. So principle of access ordering is maintained. So that's the order in which DER are managed under A&M. Most typically that is last in, first off in the UK. It could also be shared priority where multiple DER are curtailed at the same time. And essentially the operation of hold mode here has the benefit that that ordering is maintained so that when hold mode is active, some of the capacity can be passed up and down that stack. So if a high priority flexible DR starts to export more, then a lower priority flexible DR would be curtailed. And likewise, if a high priority flexible DR decreased its export, reduce the overall impact at the point of connection, some small amount of lower priority DR would be also allowed to export a little bit more to maintain the overall effect at the boundary. It also has a benefit that distribution constraints can still be resolved during the operation of hold mode. So we're not going to be risking the security of the distribution network when hold mode is activated, and it does that while also maintaining the overall effect at the boundary. And finally, just summarising up, there will not be an increase at the power, so an increase of power caused by the flexible DR at the ESO DNO boundary. So to provide a little bit of context, this diagram is a bit of an overview of normal A&M operation as is deployed on NGED's network. For each of the constraint locations that have been pre-identified in the network, we have this logical entity called a measurement point, which takes live telemetry from the network and performs some control action based off of that. So we have a number of different thresholds on the right that can be triggered. Those thresholds are triggered when the measured value breaches that threshold. We've got three displayed here. The only one we're really concerned about at the moment is the trim threshold, and that's essentially if the measured value goes above that, we're going to be sending out some real power control actions to the flexible DER, which are under the A&M control. So the little scenario you see here is that when measured values are changing, maybe due to background changes of loading, and it breaches the trim threshold, the A&M system curtails some flexible DER down to a predefined safe level, and there will be some flexible DR released up a little bit, such that there is a bit of a dead band between the unsafe range above the trim and what we try and maintain it at. So that's the general operation of the A&M system, and that will operate across a number of measurement points within the network. So when we talk about hold mode, when we enable hold mode, we're just enabling a kind of special type of measurement point. We're calling it a virtual measurement point or the hold measurement point. And instead of taking physical live telemetry from the network, it is a kind of virtualized bit of telemetry where we're taking the aggregated generator contribution to the point of connection. So looking at what each of the flexible generators are exporting, understanding through a linearized model what impact that has on the boundary, and essentially when hold mode's enabled, we set the limit that we're not going to breach to be the aggregated generator contribution at the time of hold mode being enabled. And our measured value here is just the real-time AGC. so aggregated generator contribution. And you can see the behaviour is relatively similar. So if you imagine in this situation, hold mode has been enabled, and the aggregated generator contribution is this trim line here at the start. And we see the real-time AGC changes. It changes over time. So if perhaps due to some change of generation from the flexible generators, their generators, some of those generations start to export a little bit more. Perhaps it's there's a number of PV plants and it's Dawn's breaking, then the overall AGC in real time is increasing, and we get to the point where it was at the start of hold mode, and we observe that breaching the trim threshold, and therefore we send out some control actions to reduce the overall AGC down to a safe level where there's enough of a deadband between the real-time AGC and what it was at the start of hold mode. So essentially what we're doing here is we're making sure that the overall generator contribution, flexible generator contribution, does not increase beyond what it was when hold mode is enabled. We're looking a little bit here, looking a little bit at the architecture that was that we investigated and that was implemented. So the architecture here and the communication protocols are what were investigated at the early stages of the project. What was implemented for the trial is a bit of a subset of that. We'll talk a little bit about what that means. So you see each of the different persistent domains along the bottom and the different levels there along the y-axis. So essentially up the top we have the ESO world where along here you have the ESO world, and we'll just go through each of these interfaces in turn. So interface one is the existing operational communication link that exists between the ESO and the DNO. So that is typically an ICCP link, and that we originally viewed that as not being particularly suitable for the communication of the BOA instructions and the physical notifications. And that's typically not the medium that information is exchanged through. And so we investigated in the early stages of the project this concept of how else that could be achieved, and that is through links 3 and 4 here, which were essentially viewed as another mechanism which could be in the future used to transfer that information. So we discussed this concept of a A&M data platform that would live inside the DNO's domain of control, and it would be able to use web-based communication protocols in order to get that information from the ESO. And the idea is that would be potentially more suitable because those systems would operate typically on the kind of enterprise level and be able to exchange that information in a bit more of an efficient way. And the idea would be the data platform would be able to communicate with the DNO DMS. So the data platform would do the working out of when hold mode needs to be enabled, and it would be able to communicate that signal down to the DNO, and that enable disable signal is more applicable to ICCP. Now, this wasn't implemented in the trial because some of these systems don't quite exist, and there were some questions about how that could be implemented. So that went a little bit further beyond the scope of this instance of this project. So what we implemented was the interface that went directly from the ESO control system to the DNO control system. We essentially repackaged the BOA signal and the physical notification into ICCP messages, which could be transmitted across that interface. And the rest of the interfaces here, 2, 5, and 6, are essentially interfaces that already exist and are implemented on the systems as they are right now. So 2 is an existing interface between the DNO DMS and the A&M system that operates alongside it. 5 is the 5 are the DNO control links so control and monitoring, so the SCADA infrastructure that already exists on the network. And 6 is the existing mechanism that's used by ESO to dispatch its flexible services, its balancing services, sorry. So that provides a bit of an overview of what we investigated and what we planned to demonstrate during the trial. The next set of slides, we're going to go into a little bit more detail about what the trial actually looked like, and we're going to run through some of the scenarios that run through some of the results from the scenarios that we developed during the trial. So essentially, the trial was, we took a network from NGED that has an A&M system running on it, and it's from the South Wales DNO. And essentially what we did there is we took an active A&M scheme and we extended it a little bit to make it more suitable for the purposes of the trial. So what you can see there is a single line diagram. This is just representing the existing constraints that exist up at the DNO ESO boundary. And essentially what you see here is we've got a number of constraints on the supergrid transformers. And the only other thing to just note is the DER that are on the network aren't really represented on this diagram. They're just notionally down on the distribution network. So we simulated 7 generators. 5 of those are under A&M control. 2 of those are not under A&M control. Typically, the A&M system wouldn't have visibility of them, but for the trial, we exposed some visibility there, and we would use these in order to, we would basically be using these for to demonstrate balancing requests and demonstrate the balancing service. And all these measurement points are constraint locations on the network. 1 to 8 are the constraints on the boundary. Those are real, they exist in the real world. 9, 10, and 11 were created for the purposes of this trial, added on to extended the scheme. Number 9 was a voltage constraint on a distribution network. 10 and 11 were thermal constraints on a distribution network. We have a brief overview of what the architecture that was deployed for the trial. So we deployed a number of simulation systems and A&M system as well. So the A&M system is just a typical A&M system that would normally be deployed to National Grid and to NGED in order to control generation. These servers were hosted in a cloud platform just for ease of deployment and ease of testing. And essentially the only difference with the A&M system there is that it had this more advanced hold functionality enabled on it. And we had one other server here at the top, which was the simulation server. It implemented some simulation to represent the ESO system. And so the ESO system would be issuing the data about the balancing requests, and it would be issuing it to the DNO simulation. The DNO simulation would act, represented the behavior that the DNO normally would implement, such as passing network telemetry to the A&M system and passing control signals from the A&M system to DER on the network. And then we have this box in the far right here, which represents, which we had some simulation that basically simulated the DER response and simulated the network response and allowed us to run those scenarios. We used the real communication protocols, which we discussed earlier. So the link between the A&M server and the DMS was an ICCP link, and I notice here this arrow is miscolored. We also had an ICCP link between the ESO simulation and the DNO simulation as well, in order to represent those signals passing. So all of the trial was scenario driven completely, and we looked at 20 different scenarios under a different number of different headings. We'll talk about them a little bit later. So each scenario was essentially based on historical data from the operational A&M system with some modifications to make certain situations occur. So each scenario had essentially an input profile of input data that was a time series set of data where it would change over time, and that would allow the scenarios to be repeatedly run into a system, be able to run multiple times, hopefully get the same results out. And essentially those input profiles would represent the kind of baseline DER export, and the simulation would essentially run through the baseline DER export unless there were A&M or balancing requests, and then it would essentially work out what the DER export should be based on that input set. And it would also do a fairly naive network simulation where we had sets of those input profiles representing how the points in the network, the measurement points would change over time, but it also took into account the behavior of the DER. So as an example, you would see the DER, if the DER had a curtailment request put out and it decreased its export down to 0, you would see a corresponding change of the network measurements caused by that as well. And we'll look at some examples of that in the coming slides. So the 20 scenarios were split into 6 different categories. The initial category was just demonstrating the base conflict using the trial system. So showing that when what we discussed earlier, basically, where if an ESO service, if a balancing service was issued, it would provide some headroom and A&M would nullify the request. Then a baseline, the next category was some baseline demonstration of the resolution of that conflict. Next was for during an extended service window, demonstrating how the conflict would be resolved initially and how that conflict would be maintained during different situations. And then we also looked at a further extension to that. So during that ESO service window, demonstrating how the conflict is resolved when there are distribution constraints active. We looked at some different failure situations as well, just to understand how the system would react. And then we finally ran a subset of some of those, the previous scenarios with different priorities of access, different principles of access. So the categories 1 to 5 were run using the generation, the A&M generators controlled last in, first off. And for category 6, we reran some of those under shared priority just to demonstrate some different behavior. And just demonstrate the overall behavior was the same under the different principles of access. So we're going to talk through 2 scenarios here. So these are represented by the fairly busy diagram here, the fairly busy graph on the right here, which represents the outputs from our scenarios. So this is time series data recorded from the system based on, in this case, scenario 1. So essentially, I'm going to highlight some of the things to look out for as we go through, and we'll split it into different sections. I'll just explain what you're expected to see in each of one of those sections. So the main highlights for this scenario was that we were able to demonstrate the ESO service being eroded. And we also were able to demonstrate at the end, we observed that when the balancing service ends, there was some additional curtailment actions sent out to A&M generators, which isn't ideal. You want to be curtailing them as little as possible, as infrequently as possible, perhaps. And due to the headroom that they encroached into disappearing, it caused some additional curtailment actions, which demonstrates that the kind of concept of coordination has some other benefits as well. So the first section here, most of the scenarios we started with just simulating a generator distribution constraint occurring, a distribution constraint been breached, and the A&M generators been curtailed, and this meant the A&M generators would be in a non-full release state, so that when the ESO service is requested, there is some capacity for them to release and operate under. And so I'm going to be pointing out individual trends here, but the important things to look at through all of this graph is this black line here, which is the aggregated generator contribution that we discussed earlier. So you're going to see this, and this is essentially trending the summed export of all the A&M generators over time. Down the bottom, you see the set of A&M generators. So 1 to 5, that's their export. So at the beginning, they're exporting full capacity, and you'll see that change over time as well. Other important things to note: this orange line, the green line, they are the non-A&M controlled generators. So you'll see later on that this orange line will be, you'll see it drop, and that's in response to the balancing generation turndown request. And the final things to note here are these two lines at the top. Top line is the constraint trim threshold. So that is the threshold that if a measured value for that constraint breaches, then A&M system performs some control actions on the flexible generators. And that line there is just the measurement for that constraint changing in real time. And so that's a long way to say here that you see the green line breach that trim threshold there. So that's measurement point 10, thermal distribution constraint, breaches its limit. And so some A&M generators are curtailed in order to bring it down to a safe level. And you see that there. So it goes over, breaches, A&M generator are curtailed in response, and brings the measurement value at the constraint to a safe level. There's a small amount of capacity released after the curtailment. You can see that here, and you see the measured value creep back up a little bit at the constraint, and that's essentially would be held there until network conditions allow more generation to be released from its curtailment. Now, the important thing here we see, point number 3, is that this generator number 19 has been asked by the ESO to provide a balance and service, and so its export is decreased from just over 20 megawatts down to just over 10 megawatts. So I think that's around about a 10 megawatt decrease, and it will essentially stay there for a period of time, as defined by the BO instruction. In this scenario, hold mode is not activated, and this is essentially the point at which we're able to demonstrate that conflict. And so what you see here is the distribution constraint. We also see a decrease there. So the balancing generator decreases, DG19 decreases. That causes some headroom at the constraint. And A&M system sees that, starts to release some of the A&M generators up. And essentially that has the impact of increasing the overall A&M contribution to the boundary between the ESO and the DNO. That increases up, and you get to the point here where essentially the entire turndown request from the ESO has been nullified. I think there's maybe like 1 megawatt. So the ESO looked to see a 10 megawatt decrease. They're actually, they've paid for a 10 megawatt decrease. They're actually only seeing a 1 megawatt decrease, or around approximately. And that's because the A&M system's seen additional headroom. Fantastic, there's more capacity. Release the A&M generators up, and they operate and they maintain when they see the headroom reduced. The final point to mention here is just that second point we looked at the highlight slide, where we see some additional curtailment from the A&M generators, where essentially because they've eroded into the headroom that the ESO request provided, when the ESO service ends, generator 19 potentially going to ramp straight back up, and that causes an additional curtailment event at the distribution constraint. which causes the A&M generators to be curtailed again. Whereas if we had resolved the conflict and didn't let the A&M generators release, that wouldn't have happened. So some potential parallel benefits there. So overall, demonstrating the conflict, we were able to see the erosion of the balancing request due to A&M actions. So we're next going to just look at scenario 11, and it's essentially hopefully ideally shows the benefit of hold mode, shows the ESO service not being eroded, and shows that the A&M aggregated export can be maintained. So that the points to highlight here, so we do enable hold mode. The aggregated contribution of the generators is held at a steady state throughout the hold mode. We also continue to manage distribution constraints during hold mode. So this is a bit of a longer scenario. There's a bit more happening, and it's important to also see that when possible, DER released as well. So flexible DER released when there's capacity that's not going to breach the hold mode limit. So again, this scenario starts quite similarly to the previous, where we see a distribution constraint. We simulate a distribution constraint occurring, so the A&M generation is curtailed a little bit in order to give them some capacity to release into. And so you can see that there, we've got high level point there, high level, the top line is just the trim for the distribution constraint. So the overall threshold, the distribution constraint that the A&M system operates on. The kind of red line there is just the measured value at the distribution constraint. We're going to see that it's going to go and breach its threshold a couple of times. But the main thing to notice here is initially, distribution constraint breaches its threshold, A&M generators are curtailed when that happens. And you can see the aggregated contribution of the A&M generators decreases down and then is held at a steady state. This box is a little bit too far to the left. Apologies for that. So if you imagine this box just slightly bit further to the right, we're seeing the balancing generator. So DG19 again is ramping down. So that's in response to the service request from the ESO. So we see that ramp down, and we see an increase of headroom at the distribution constraint. So in the previous scenario, this is where the A&M generators would continuously ramp up, completely erode that request. However, that doesn't happen. So hold mode is enabled at this point. And what we're going to see here is the aggregated generator contribution is going to remain relatively constant through the entire duration of the ESO service request. So this generator 19, so the ESO service request lasts from here until the generator 19 ramps back up. So at this point, hold mode's enabled. And the key thing to note there, let's go back, is that if we look at this line here, so at the point where it's enabled, we see the aggregated generator contribution remains fairly constant through it all. It dips down a few times. That's due to distribution constraints we'll talk about in a second. But the important thing is it remains fairly constant through the duration of the test of the scenario of the ESO service request. So point 4 here to note is that we simulated some additional constraints occurring during the service window. So we simulated some changes in the background loading, which caused the distribution constraint to breach its threshold again. And essentially what we want to demonstrate here is that the A&M system will continue to manage its A&M generators in response to distribution constraints. So we see a thermal constraint breaching here. A&M generators are curtailed in response. You see the aggregated contribution decrease because the A&M generators have been released. And And the important thing to note here is that we do release the A&M generators back up when it's possible. So the A&M generator, so if we imagine that was a transient issue on the distribution network, A&M generators can be released back up, but they're not released beyond the limit at the start of hold mode. So showing that A&M generators can still be released, but they're not going to be released more than what they were doing in total at the beginning of hold mode, at the beginning of the ESO service request. It's not quite represented in this diagram. There were too many trends already, but during this scenario, we also demonstrated a voltage constraint on the distribution network. And essentially what we saw here was the, it's not on this diagram, but a voltage constraint occurs, A&M generators are curtailed again. You see the decrease and the ramping back up when the constraint is resolved due to the background conditions. And at the end of the scenario here, you see the A&M generation is the ESO, service ends. So the generator 19, which is providing the service, ramps back up, and that removes the hold requests from the A&M generators as well. So they can ramp up and do whatever they like, as long as the distribution network constraints allow it. So just to summarize here, there's a lot of content in the slide. The main thing to be looking at here is the aggregated generator contribution. It doesn't increase from the point it was at the start of when hold mode's enabled, when the ESO service is enabled. One of the other key learnings from this scenario, or from some of the scenarios here, is we do see a small amount of degradation of the ESO service. So much smaller than when there's no hold mode. We see perhaps about a megawatt of a difference. So we look at this line and this line here. So there's about a megawatt of a difference there. And that's essentially due to the time it takes for the balancing generator to ramp down. So depending when hold mode is enabled, if there is a gap between if the balancing generator starts to ramp down before hold mode is enabled, you may see a small amount of erosion from the A&M system. So one of the things we want to look at in future work is to understand just exactly how that can be minimized. But there was a very useful bit of learning from this set of scenarios to see that when you're looking at real-time operation, the timings are quite important, and you need to look at when hold mode's enabled there. So trial learnings, for a brief overview. I've mentioned some of them as we went through. We'll talk a little bit more detail about them. So essentially, the first one is fairly obvious. There can be some unavoidable conflict where sometimes if an A&M generator is providing services to the ESO, that sometimes they will be curtailed. And that kind of goes a bit, it's not really what we're investigating here, but we're able to demonstrate it. So if an A&M generator is providing some sort of service, but there are distribution constraints, then they might not actually be able to provide those services when it comes to it. And that's a little bit more likely when they're in last in, first off. When it's shared priority, there's a smaller chance that each individual generator is going to be completely curtailed. So that's a little bit outside of what we're investigating overall here, but there's some useful things to point out. We did identify quite a bit of complexity around data mapping. So looking at the identifications for DER inside the ESO world, they're likely to be different from the identifiers used by the DNO. So there's certainly a mapping exercise that's going to be required there. In the earlier slides, we talked about this concept of a data platform where there could be a system used to perform that mapping, a system used to do some extra functions that wouldn't normally happen on the control system. So various potential mapping around data identifiers. We also were able to identify there's a fair bit of complexity around signal exchange. So some of the information that needs to go between the ESO and DNO is difficult through operational protocols such as ICCP. And again, that feeds into our thoughts around about having a kind of separate platform for communicating that data. Another important learning that we were only able to identify through the trial is essentially that last point I made in the previous slide. So we see a small amount of service degradation due to the ramping of the balancing generator. So if the generator starts to ramp before hold mode's enabled, then the A&M system will see a little bit of headroom and will start to ramp up A&M generators before the hold mode actually becomes active. Then we've got a few things we can do around that. I think we talk about that in the next slide, but the degradation, the erosion of the ESO service is considerably smaller. And the final point is you also see with hold mode, with the coordination, you do see a reduction of curtailment events when the ESO service request is ending. I'm going to be passing on to someone else to cover the commercial evaluation and learnings.
Thanks, David. So just to say, so WSP also undertook a financial and commercial evaluation to try to understand what would be the implication of making these changes to the A&M. And we did this taking into consideration the Access SCR, which is the forward-looking significant code review. The approach that we adopted to do this was first to review the Access SCR document itself, and also to engage with subject matter experts at the distribution network operators, and to identify data that will be required for us to undertake this evaluation. So some of the quick learnings and challenges that we've realized is through these, what we see is that there might be a potential loss of revenue by the generators themselves that are part within the distribution network operator. Due to the changes that are being proposed, it might be possible that DNO or ESO could incur additional costs in order to maintain the balancing service headroom. And then the last challenge that we had was in order for us to quantitatively analyze the financial implications, we required some data and also the commercial evaluation. But soon it became apparent that this data might not be available because either the DNOs and ESOs do not collect this sort of information, or in certain cases, it would be unknown. For example, the DNO would not know what a generator would export. So these were some of the challenges that we came up with. Thanks, David.
Can you go to the next slide, please? Cheers. So just a bit of context sort of from the ESO side of things, how this type of a system could be useful to our control room colleagues. As Mazza alluded to at the beginning, the DNOs are deploying more A&M systems, and there is that growing need for NG-ESO to procure from embedded DERs. For instance, in the southeast and southwest regions, there is, over the next few years, there's a significant amount of DERs that are potentially going to connect as a result of the Deep Connect and Manage, where which was a program to see how we could increase the number of generators that are connecting onto the DNO network without incurring that cost of reinforcing the transmission network. So these visibility and control terms were added to the terms of the generators in the southeast and southwest regions for them to, requires them to give visibility, operational metering, and the ability for the ESO to turn them down in case there's a constraint in that area. These generators could, that control could be achieved either through the BM, so they could join the BM, or the ESO is developing a service, Megawatt Dispatch, which is a cheaper option as opposed to the BM, in order to provide that visibility and control. And so if you look at, for instance, the southeast region, you've got a potentially significant amount of solar that is going to be connecting over the next few years. And also in that area, you also have that interconnector coming in from the continent that could create a difficult constraint to be able to manage. And the ESO would need to dispatch to DERs connected that are distributor connected in that situation. So this system could prevent those ANMs that are connected within that region from eroding that service, as David Smith has shown, which would potentially lead to a more efficient operation of the system from our control room. Aside from that, this type of system as well could go hand in hand with the work that's being done to produce primacy rules. So if you have the ESO and the DSO procuring services at the same time, then potentially an algorithm could be written in this type of system, because essentially it's acting as a kind of a middleman, and it could implement those primacy rules in that situation. So yeah, happy to move on to the next slide.
Thanks, Dennis. So the conclusions and next steps for ourselves, obviously we've shared the findings today, and we'll follow up with the Primacy Rules Group and ANM systems developers to make sure that they've had copies of the information, that they haven't got any further questions. We'll be publishing the recording from today and the slides on the NGED Innovation Portal, so they'll be available to people who weren't able to tune in today. And we'll be publishing the closed down report in the next few weeks as well. And then in terms of BAU rollout, we really want to firm up the cost benefit analysis first. As Dennis said, there was some information, sorry, as Maz said, there was some data that we found that we didn't have in terms of the operation of the ANM systems currently, to give us an idea of how frequently these conflicts are likely to occur and what the impact of those would be. But post-Access SCR implementation, we are expecting there to be improvements in the data that's available to carry out that assessment that will help us to firm out those rollout costs and benefits. And as Dennis mentioned, we do need to compare this to dispatch and coordination alternatives from the 1 megawatt dispatch and other options. So that concludes the presentation for today, and we can move on to the question and answer portion of the event. And I can see that we've got some questions waiting for us. So that first question in the list comes from John Stapleton, and it says, in hold mode, what are the potential contract or commercial implications for generator 2, which is being curtailed, which is connected under a flexible connection agreement? So I'll throw that open to the team. I think it probably comes under the lack of complete data item that we raised earlier, but I'll throw that open.
There is a bit of a commercial aspect as to the reason they're being curtailed. So it's less, so they're being curtailed not so much because of a distribution constraint in this case. It's been because there are ESO services active. So I can't quite answer that. I think it would depend on the exact connection agreement that's in place with them. However, the LIFO ordering is still maintained, so that aspect of it is fine. And I guess what I would highlight is they're not being curtailed in response to the ESO, the balancing requests. It's only that existing curtailment is potentially being extended for the duration of the balancing request. So it's not like they're being curtailed in response. It's just that curtailment is potentially being extended out if they were curtailed beforehand to stop the headroom from happening.
Okay, the next question is, as part of the project scope, are you designing and delivering an automated method of sending ESO service information to DNO, as opposed to the DNO logging onto the ESO portal to manually extract the data?
So we didn't, I can answer maybe that a little bit. So we didn't look at a kind of solution on the ESO and DNO side to make it happen in their kind of enterprise infrastructure. But we did demonstrate that those signals could be transmitted. So there was no manual logging on and looking at things. There was the data transmission was through a communication protocol, could be automated. It's just a matter of adding those integrations into wherever that data lives. So to answer that kind of.
Yeah, okay. And then the next question is from David Hawkins. It says, you've indicated that ICCP wasn't suitable for passing the instructions and showed an idealized architecture. However, you implemented instructions via ICCP. Please will you explain the unsuitability of ICCPs versus the systems that don't exist?
Yeah, I can answer that as well. So what we did with ICCP there is we used one of the blocks that isn't traditionally used very heavily, and we've got some questions about how many of the control systems out there actually use it. So we're using the information message block, which essentially allows text-based information to be passed through. So what we did there is we took the BOA instruction as it is transmitted out. And we did a small transformation to make it a little bit easier to parse, but then essentially that was sent through the messaging infrastructure, the messaging part of ICCP as text, and was then parsed on the DNO side. So it's not particularly suitable because that's not very heavily used, maybe not heavily supported, and also the systems that those ICCP links live on aren't necessarily where that data is coming from. So you would be having to bridge wherever the ESO, wherever in the ESO world that those requests, that information lives, into the operational infrastructure where the ICCP infrastructure lives. So there's some additional hops there and things that require quite a lot of potential infrastructure changes.
Okay, thank you. Then we have a question from Matt Malcolm. On GSPs with multiple users, how is it determined which user the signal is passed to?
So I guess it depends. Are we talking about multiple A&M systems operating, which I think is something we don't really consider and isn't really a thing that happens. If we're talking about multiple DER, flexible DER in the network, so that the hold signal is passed to the A&M system itself, and it would then use whichever control orderings it has as standard. I'm not sure if that answers it.
I think so. Then we've got two questions that both relate to interactions between distribution and transmission A&M systems. So it might be worth asking both of those questions to see if there's a common answer that explains that. So Mohammed Demi asks if there are two CCPs installed in those sites which are under distribution A&M and transmission A&M. If yes, can there be one installed so that it can be programmed to meet distribution and transmission A&M requirements? And then Teresa Evans is also asking, will this work with transmission A&M combined with distribution A&M and potentially different A&M service providers within the one DNO area?
I can some thoughts on that. So that's something that would potentially be something good to look at in future iterations of this. So the suitability of the control algorithm of this kind of control algorithm for multiple A&M systems hasn't really been considered. So I can't provide a good answer there, but it's something that could be investigated. I don't know how common that is. That's potentially a question for NGED about whether there will be either multiple CCPs for different CCPs for distribution A&M and transmission A&M, or different A&M systems for distribution A&M and transmission A&M. Certainly for the scenario we've looked at here, it was the same A&M system controlling the constraints at the transmission, so the transmission boundary, so supergrid transformers, and the constraints on the distribution network. And that's really all we've been looking at as well in general.
Okay. Then we've got another question about whether DER represents distributed control and demand response as well.
So what we were looking at as part of this trial was the balancing generation turndown requests. So for this trial here, we were only looking at distributed generation. However, there could be situations and potentially other services which could have conflicts arise, where there would be conflicts because of demand response, but that wasn't part of this, the scope of this trial.
Okay. We've got some detailed technical questions on the hold mode. I'm just going to skip on to some more general ones. Have you considered the impact of DER communication system failure on constraint management? For example, a BT OpenReach or cell phone network outage, or during cold start or system restoration? Well, we appear to have lost your audio, David.
Oh, yep, I pressed the button, sorry. So some of the scenarios we looked at did include failure scenarios. Those were mostly failure scenarios of kind of subsets of, say, the communication infrastructure, or subsets of the A&M system. It wasn't necessarily DNO-wide failures. So that wasn't part of this, the scope of this, but essentially you do need some telemetry in order to do control. So I think that would be covered by existing failure cases, fail-safe behavior.
Okay. Similarly, the question's been raised, have you considered the possibility of service stacking, where a DER provides some services to the DNO and another service to the ESO? I kind of feel like if it's service stacking, that they would be operating in the same direction.
I think that'd certainly be something that there would have to be a fair bit of interaction there with the service provider to understand exactly what they're doing, and the coordination is really up to them to do their own coordination. I know there are some situations where we did mention it, where there's a situation where you've got a flexible A&M control generator providing services to the ESO. I'm really sure that's pretty much up to them to make sure that the services they're bidding in for are not going to be causing, they're going to be able to meet.
Yep. Then we have another question about the opportunities for participants that might be offering an increase in generation. So the question is, was the only consideration to generation reduction? Is it not envisaged that BM participants might be able to offer an increase in generation in a network area covered by an A&M?
Yes, it's possible. It wasn't the conflict we're looking at as part of this trial. There may not be much conflict there. To be honest, it was decided we would look purely at generation turndown requests. The problem is if they're performing generation turn up and that triggers a constraint, then that kind of falls into the kind of primacy rules territory of, well, if they're causing the constraint themselves, then if you don't want people off supply, there's going to have to be conflict there if they're causing the constraint. But certainly it is something that that can be investigated.
Okay, and then a follow-up question from Matt. What about A&M systems that cover a wide range of distribution network constraints on the 132 to 33 kV distribution network, where curtailment under the A&M systems are applied based on generator contribution to a given network constraint rather than purely LIFO? It seems the concept of a hold mode wouldn't work as described for these systems.
So that is essentially what we were demonstrating here. So so the scenarios we looked at were fairly high level scenarios, but we did have scenarios where there were either generators in the distribution network that weren't necessarily related to the boundary, and we demonstrated they could still be controlled and weren't impacted by the hold signal. And what I would say is that when we're calculating that aggregated generator contribution, we are taking in the relationship that takes account of the relationship between the DER and the boundary as well. But yeah, so the scenarios we're looking at here were covering those voltage ranges.
Okay. So if we come back to the more technical questions then that were asked by Raphael Walker, he had a question on how the hold mode is enabled. So his first question is, how is the hold mode enabled? Is this automatic following the ESO service request, or would it need to be manually enabled on the A&M system?
Yeah, so it's what we looked at was automatically enabling it. Yeah. So and that was one of the things we do have to consider and look at is the timing of that, and whether the information we receive is sufficient to effectively do that. So potentially you may want some additional information about the ramp times for the generator providing the service. Then you can understand exactly when you need to enable hold mode. So there's potential ways, and I think that's something we've described in the close down report as potential future things to look at is how that can be made more efficient.
Yeah, and his follow-up question is, does the hold mode hold all existing trim thresholds, or does it hold generators under A&M control at the level they are actually exporting at the point that it's enabled?
Neither. The second one is closer to it. So on the face of it, it controls them at the level they were exporting when it's enabled, but there is flexibility when hold mode's enabled for that capacity to be shared around following the LIFO ordering, or whichever priorities of access they're defined.
Okay, and then we've just got a last couple of questions. Will the deck to be issued include indicative timescales for deployment? I think it's more likely to be showing the next steps in terms of further investigation rather than the timescales, because I see you rightly suggest, Jim, that it does link in with the Open Networks projects and future developments there. Is there anything that the team wants to add for the timing of BAU rollout? No? Okay. And then the last question, I think, then seems to come from Matt Malcolm. GSPs, rather, that feed multiple DNOs or customers so that the A&M doesn't look at the entire GSP flow. I'm not quite sure we interpreted the question correctly there. But I think that the issue is that the A&M doesn't see the entire GSP flow. Is that an issue? Is that a problem?
There's probably a more fundamental question there about how that's managed in general, how the A&M system manages that in general for those situations. What I would say is that the relationship between the DER and the boundary that you're controlling it takes into account what the contribution is. So if you have a DER that it takes into account what impact the DER is going to have. So if it's not a fairly one-to-one relationship, it does take that into account.
Okay, and that brings us to the end of the list of questions. Thanks very much, David. Difficult to be put on the spot there. So I think it only comes to me to just to say thank you very much for joining us today. Thanks for your interest and the questions. As I said before, we'll send on the link to the recording once it's published on our website, along with the slide set. And all of our contact details are there on the screen at the moment. So if you have any further follow-up questions, you're able to contact us. So thanks very much, everyone.